Yeah. So in the last class, we discussed or defined the problem of probabilistic inference, right? So you have knowledge base, which is kind of defined based on different probabilities. And basically, we have a Bayesian network where you have got conditional independence assumptions. And for each node, you have a conditional probability table. And given that you have a Bayesian network, there is a variable set V, and from this you have one variable that is designated as a query variable, and a subset of these variables, they are evidence variable, and the remaining subset is our hidden variables, right? Now with this definition, let us try to talk about how to come up with algorithms for performing this inference, right? So let's say I want to compute something like this. So you have, so this is a task in your hand, probability of X given E. So let us just think that we have only a single variable that is your evidence, right? So the first method that we are going to discuss is what we call as inference by enumeration. So here we will be enumerating all possible values of the hidden variables and try to compute what we want. And in a sense, this is a kind of a brute force approach, right? And we'll see that if we take a brute force approach like this, so we will not be having an efficient solution to the problem that we have in our hand, right? Now, this conditional probability is something that we want to compute. Probability X given E, where X is the query variable, E is the evidence variable, right? And how do we compute that? We just compute the joint distribution of X and E and divide that by, normalize that by P of E. So this is the definition of probability X given E, right? Now, what we can treat these to be a kind of a factor which does not depend on anything else. So we can say that alpha is equal to 1 by PE and keep that here, right? So this is just for the sake of writing the expression very easily. And what we are remaining with? We are remaining with probability PXE, right? Now let's say we have a hidden variable Y. So this variable was not there in the query or in the evidence, right? Now, how do we write this joint distribution? This joint distribution is basically a sum of the joint distribution PEY. And this Y can be having, if we are treating this Y to be a binary variable, so in one case it will be plus Y, and in other case it will be minus Y, right? So basically you'll be computing probability X E plus Y once and probability X E minus Y once, and then sum them up to get these value, right? Or basically these value. So basically this, what we are coming up with, this probability X given E is proportional to the joint distribution of PE, right? So this is the kind of assumption, or this is the kind of formulation that we are starting with, right? Now, this is the given Bayesian network where the alarm is dependent on the event of burglary and earthquake, and whether John calls or Mary calls that depend on this alarm, whether this is going off or not, right? And from this, what we want to compute? We want to compute what is the probability of there is burglary given John and Mary calls. So this is what we want to compute, right? Now again, how many variables are there? We are having 5 variables. We have got B, E, A, J, M, right? Now out of this, B is the query variable, and J and M, they are our evidence variable. And what are the hidden variables? The hidden variables are E and A. Now, how do we get this probability? So this is again is proportional to this joint distribution of B, J, M, E, and A, right? Now, as we are these values are known to us. These values are known to us. So we want to set them to be all true. Only other variables that will be having different values are the hidden variables E and A. And how do we get this conditional probability? We'll be iterating over different values of E and A to get these values, right? So this is the kind of strategy that we are taking, right? Now, how do we factor this? We can factor this using the dependency that we have in our Bayesian network. So I can write this as probability B, probability E, then probability A given BE. So from this node, and probability J given A, probability M given A, right? So this is the kind of computation that I need to do, right? Now let us try to see how many products that we are doing here, how many multiplications we are doing here. Any idea? So we are doing 1 multiplication, 2 multiplications, 3 and 4. So in the inner loop, we are doing 4 multiplications, right? And how many times this loop is, so you can think this to be a kind of nested loop, right? And for each of these, how many values are there? We are having 2 values. And for each of these 2 values, how many values are there? We are having again 2 values, right? So the total number of multiplications that you are doing here is exactly 2 to the power 4 multiply 4, which is in the order of 60, right? Now let us try to compute another factor, say probability of J. I'm not conditioning on anything, right? So in that case, what is our query variable out of these 4? Our query variable is only J. What is the probability that John calls, right? That means all other variables here, they will be treated as hidden variable. And as their hidden variable, we have to iterate over all the possible values for these variables, right? So that's why we have 4 summations. And in the inside loop, we are having the same factors, same number of factors and same number of multiplications, right? So again, we are having 4 here, and will be doing how many such products? So it will be 2 to the power 4 multiply 4, right? So the total number of products that we are doing here, 2 to the power 4 multiply 4, and basically it is in the order of n multiply 2 to the power n, right? So this is the number of products that we are doing. Again, this is not really tractable if you have these n to be very large, right? So the question is, can we do better, right? So we started with this. So this is the very basic way of enumerating all the possible values of E and A, right? So one can notice that, well, so this PB is not in the scope of E and A. So what we can do, we can safely move this out. Now, if we move this out, you can see there will be a number of multiplications that will not be doing, right? So you can see how many number of multiplications that we can avoid if we can take out PB from this place to this place, and we can do that, right? Now, if you think about PE, it does not depend on probability. It does not depend on A, value of A. So what we can do, we can take it out of the scope of A variable and put it here inside the scope of E, right? So in this way, we can avoid some of the multiplications. So we can rewrite these, the same thing as these, a probability B multiply summation of probability E, and then we have got all the factors. Those are having A as a variable. So we cannot do better than this, right? But again, we have reduced the number of multiplications by moving different fragments or factors in different portions by looking at the scope of the hidden variables, right? And if you can do the same for the other problem, what is the probability of John calling? you can factor these as we have written here, right? So you are having A, we have moved A out there, and we are keeping this inside the scope of A, and this probability MA will be both in the scope of M and A. Probability B will be only on the variable B, and the remaining remaining factors will be scoped under E, right? So the point that I'm trying to make here, that you can look at the factors and shuffle them in certain way so that you can avoid some number of multiplications which are not really necessary, right? And if you can have a closer look at it, you can see you will be having only 2 to the power 4 products, and which is in the order of 2 to the power n. So earlier we had order of n multiplied 2 to the power n. We have done a bit better, but not really that better. So still we have this 2 to the power n, right? Now, if we want to make it more efficient, so let us try to observe something. So what I'm trying to show here, it's a computation tree of the computation that we did earlier, right? So we are computing this probability B given J and M. And how do we compute this? So we are computing this in a top-down manner, right? So we have this probability of B, right? Then what we do? We sum up the probability of E and probability of not E. So in this place, what we have, we are summing up probability of E plus E probability of minus E, right? And inside this, the scope of A, what we are doing, we are multiplying probability ABE. So here we are having the variable to be A. So now we have to replace A with plus A or minus A, right? And we'll be having different factors. And as we are having different factors, we'll be having different branches that we are following. So depending on which sign that we are following for A, we'll be having different branches. So now here we are following the positive value of A, and in this branch we are following the negative value of A, right? And finally, we have positive value of A here, positive value of A here, negative value of A here, negative value of J here. And the factors are now computed one by one, and finally you are getting the final product. So you can see it very simple, right? The thing that I want you to observe in this kind of computation tree is that certain part of this computation tree is being calculated time and again. So for example, this product you can see this is computed twice, here and here. This product is computed twice, right? And if you can take other examples, you may see that there are different substructures that are being computed time and over again. So what we can do here to save time and as well as space, that why don't we compute, I will not say time, space also. I want to save time, for example. Now, why don't we compute the value of a substructure or a factor and save them so that they can be used later? So does that strike something to you? Similar kind of approach have you considered earlier, specifically those who have done algorithm course? Any idea? So what I'm saying, that I am computing a small, or I'm solving a small part of the problem. Basically, the problem is try to come up with the value of the product, right? And in doing so, I'm computing a part of the computation. I'm doing the part of the computation. And I want to save this so that while this computation is getting repeated, instead of doing this product, I'll just retrieve the value and use it directly. And we are saving number of products in such a way, right? So what I'm asking, do you know any approach, any kind of approach that has similarity to this kind of strategy?
Sir, dynamic program.
Exactly. Thank you. So basically, we do similar thing in dynamic programming. And we know that dynamic programming is very efficient in the problems where the problem has got substructures, similar substructures, and these substructures are computed and solved first, and those results are saved. And these results, when they are necessary, they are being retrieved from the database, right? So exactly, we'll be using similar kind of approaches. So what we'll be doing, we'll try to eliminate uh, the repeated calculations, right? So we'll be computing it once and save the result for future use. And that is what we follow exactly in dynamic programming, right? Now, whenever we are doing the summation, right, we are doing sum over a single variable, right? Now, when we are doing that, so when we see that, let's say we are doing this sum over A, we are doing this for the cases or for the factors which has got these variable apart from others, say P, B, something like this, right? And we just ignore the others. Let's say we have something like PE. We do not really take into account P while you are computing the sum over A. We have it in some other place, right? So that means we have got some number of factors. So these are the probability factors. And what we want to do, we want to come up with an efficient way to compute the entire product by considering the multiplication of smaller factors, right? So let us try to see what we mean by factors, right? So initially, we consider each of these probability that we want to multiply to be a factor. So this is what we name as F1B. So B is basically the variables that are involved in this factor, right? Now this is again, it's a factor of E. We name this to be F2E. Now this A, B, E, this is a factor of three variables, A, B, and E. We name that to be F3E, right? I'll later talk about what we mean by factor and what are the kind of operations that we can do on the factors, right? Now let us look at this probability JA. So basically what we are given with, the fact that we assign the value to J. Let's say positive value J. So this J is no longer a variable here. So only variable that we have here is A, right? Because it only depends on A, it does not depend on J. That's why it is a factor that is defined over A. And similarly, this is a factor that is defined over A, right? Now we'll be forgetting about all this probability, conditional joint, etc. We'll be playing with factors. Now, how do we represent these factors? We represent these factors again with a multidimensional array. Multidimensional array. So if you think about B, B is basically whether there is burglary or not, right? We have got two values, right? E is whether there is earthquake or not. We are having two values. How do you define F3ABE? So that is basically probability of alarm given BE, right? And how did we represent this? So this is basically a 2 cross 2 cross 2 array. Why is that? Because every variable will be having two alternatives. So that's why it is a 2 cross 2 cross 2 array. And what are the kind of values that we can have? So let us think about, so what is the value of A, B, E in the, say, first position, 1, 1, 1. So can anybody tell what would be the value for this? So basically it is representing a conditional probability table, right? So you have got B and E, and what we represent, A is true given BE. The other value is A is false given BE, right? So one value could be this is true, and this is having a value, this is having another value, right? So basically it is a 3D array, and each dimension of this will be having two different values, right? And how do we represent A4A? So basically two values, like what is the probability that John calls given the alarm rings, and what is the probability John calls alarm does not ring. And of course, for F5A is kind of similar, right? Now, I hope that you can see the association between these conditional probability tables with these factors, right? So is there any doubt or question at this point? Because now we'll be playing with the factors. Good. So now we can rewrite this expression in terms of factors. So basically, this will be replaced as F1B, F2E, F3ABE multiply F4A multiply F5A. Now this multiplication is a different kind of multiplication, which is a kind of point-wise multiplication. So it is not a normal matrix multiplication. We'll come to that. With this notion, what variable elimination algorithm does, it parses or it considers the whole expression from right to left, and it interleaves the product and the sum operation. First is perform product, and then it performs a summation over a variable. Then it goes for performing another product and then perform a summation. So let us see what I'm trying to mean. So we'll be taking the same example. We are having these factors, and out of these factors, I want to come up with the value of probability B given Jm, right? So the first thing that we'll be doing, will be scanning this formula from right to left, and we'll be computing these product first, right? And then we'll be summing over the product on this variable. So this is the first operation that we are doing, a product followed by a sum out operation on A, right? So how will it look like? So we are doing this product and we are summing out on A. So what is the variable that we are eliminating here? So we know that if we sum out on a variable, that variable will be eliminated from our formula, right? So summing out on A, this implies A is eliminated. And what this variable elimination algorithm does, it takes a variable in a particular order and tries to eliminate it. And what are the variables it will be eliminating? It will be eliminating only the hidden variables, right? And that we'll be doing in a specified order, right? We'll be talking about the order later, right? Now, how do we compute this? What are the values A can take? A can take either plus A or minus A, right? And if we consider A to be positive, then we have these product, which is F3A given BE, F4A, F4, F5A. And if we consider A to be negative, so we just replace A with negative A and we have got this, and then we sum this. If we sum this out, the output is another factor without the variable A, because we have eliminated the variable by considering all the possible values of that variable, right? So that is what we call as sum out operation on A, right? Now, what is the resulting expression we have? The resulting expression as we have this entire summation replaced with F6BE, right? Now, what we will be doing? We will be performing this product and then we'll be summing out on E, right? So as we do this, what kind of expression that we will be evaluating? We'll be evaluating expression. So E again can be positive E and negative E. So you'll first replace E with positive E as we did here, and then we'll be replacing E with negative E as we have done here, right? This means we are eliminating the variable E. Now, if we eliminate the variable E, what we are left with? We are left with a factor without A and E. So this is without A and E. And what are the A and E's? These are hidden variables. And the strategy that we are following is that we will be eliminating the hidden variables, right? Now, finally, we'll be computing this product to get this probability B given Jm, right? So this is the kind of strategy that we'll be following. So let me go to an example that will try to make the thing more clear. But before that, let us talk about this pointwise product operation, right? So what we have for the product, we have got two factors. So let's say one factor is having xi to xj variable and xy1 to yk variable. So these are the variables that are associated with f1. And with f2, we have these variables associated with y1 to yk, z1 to zl. Now, if we perform the product of these two factors, so the output factor will be having the variable to be union of these variable sets. So the union of these two variable set is x1 to xj, y1 to yk, z1 to zl. So what does that mean? So here we have, say, 2 to the power j plus k assignments. Here we have got 2 to the power k plus l assignments. As output, we'll be getting 2 to the power j plus k plus l assignments, right? Now let us look at these example, right? So here we have one factor f1ab, which is already defined, right? The values are already defined. Another factor which is defined on bc. Now, if we want to compute the product of these two factors, so the variables that will be associated with this product will be A, B, C, right? Because we are taking union of these two variable sets, right? And as a result, the values for each row. So what we are doing, we are taking this row and then doing a pointwise multiplication. And if we do pointwise multiplication, we have got 0.06 here. And as the assignment of ABC, it will be true, true, and true. So let us take any other. So let's say F, T, and F. So take this F, T. So we take this row. And we have got, say, TF, this row. If we perform a multiplication pointwise product, it will bring us 0.72, right? Now let's say this is the kind of product operation we have done. Now we'll be summing out on A. So let's say we are doing the sum out operation on A, and what will that get us? It will eliminate A, right? So for that, what we'll be doing, we'll be replacing A with positive A and A with negative A, and we'll be adding these two factors, right? Now, let us try to find out the corresponding values, right? So if we set A equal to, so in this factor, we are setting A equal to true, right? So what are the values B and C can take? B and C can take both true value, and for that what we have got this 0.06. We put it here, right? Then we have got T and F, right? So B is true, C is F. So this here we are having C, negated C, and in this rows we are having this B and negated B. So what is the contingency for B and not C? B and not C for A equal to true is 0.24. Now we have got this 0.24, right? Now here what we will be computing? We will be computing not of B and positive of C. Not of B and positive of C. What is the value here? 0.42. We put 0.42 here. And similarly for the other contingency, not B, not C, we will be having 0.28, which is basically this value. Similarly, this matrix represents the factor F3 not of A, B, C. Right? Now, if we add these two, this is the kind of matrix that we are getting, which is basically representing the factor FBC. And here we are eliminating A. And I hope this example makes this idea of multiplying two factors and followed by that doing this sum out operation and getting a new factor clear to you. Right? So any doubt or question at this point? Okay, good. Now, in some point of time, I was talking about variable ordering. So in variable elimination, what we are doing really, we are picking up a variable, hidden variable, and we are eliminating on that. And then we are taking the next variable and we are eliminating that. So we had ordering involved in that. So in the earlier examples, we have taken, say, E followed by A, right? So in the first example, we have taken E followed by A. Now one might ask whether A followed by E will also work. So actually that also will work. So the outcome of the probability value or the computation does not really depend on the variable ordering. I guess I have made a mistake here. So here I think we'll be having A, right? So here we are following the ordering E followed by A, but here we are following the ordering A followed by E, right? Now you can see that here when we are following the ordering E followed by A, we have got three factors which we are computing together. But here, when we are talking about A followed by E, we are computing only a product of two factors, right? But the first point that I like to highlight is that each of these ordering choice is valid. But what different ordering choice will lead us to? It will lead us to different factorization. As we can see here, we have got a different factorization here than this, right? Now, one thing I'm not going to prove, I'm just stating by just relying on the literature that the time and space requirement while you are computing this is determined by the size of the largest factor, right? So it might so happen that you come up with a ordering where you are, say, multiplying 5 factors together. And for the same computation, you come up with another ordering, the largest factor size is, say, 2. Then the space and time complexity for this would be much less than these ordering. So while we are talking about ordering, we should try to find out the ordering for which we have optimal number of computation. And finding optimal ordering is really intractable. That is a kind of a hard problem itself. And there are different heuristics that are used to come up with ordering that will reduce the time and space requirement while doing this product. Right. There is another idea that is associated with variable elimination. That is what we call as variable relevance. Right. So let us try to think that we are computing what is the probability that John calls given there is burglary. So you can design the factor like this. Here we are having one additional variable m, right? And the product that is the factor that is involved with this variable is PMA. Now one can observe that while you are doing sum out operation on m, this m can take positive and negative value. And if we add them, we always get the value 1. What does that imply? That implies if we plug in that value here, this variable does not have any relevance. Why is that? Because the probability J given B remains unchanged if you remove this altogether. This the variable M is no longer relevant to the computation of this, right? And as a matter of fact, any leaf variable that is not a query variable or a evidence variable that can be safely removed without any effect in the computation. And if we go further, basically every variable that is not an ancestor of a query or an evidence variable, they are relevant to the query. So even it is not a kind of leaf node, every variable that is not an ancestor or query variable of an evidence node or a query node, it can be safely removed because it will also become irrelevant. So let us try to go to some examples to illustrate the ideas further. So first, I will try to come up with different factors related to a given joint distribution, right? So let's say we have this temperature and weather joint distribution as we have seen earlier. Now, first we can compute a factor which we call as selected joint. And in selected joint distribution, we specify a value of one variable and leave the other variable uninstantiated. And basically here we are slicing this particular joint distribution and picking up that slice to bring this factor, right? You can define a single conditional where we condition a variable and the condition variable and the given variable is assigned a value. For example, I am assigning a value T to be cold, right? Now, given T is cold, what are the probability of different weather values, right? So that we can compute to be 0.4 and 0.6. How do we compute it? We just compute the probability of W T given cold. And what is this? So you can look at sun, right? For sun, we have this particular row, which is 0.2, right? And divide that by probability of cold. And what is the probability of cold? The probability of cold is summation of these two, which is 0.5. So 0.2 divide 0.5, which gives us 0.4. Similarly, you can compute probability rain given temperature is cold, which is 0.6, right? We can extend this to compute the family of conditional. So here I'm not providing any value to cold. So this part we have already computed. And similarly, you can compute the same by conditioning T with the value hot. So we'll be having this value, right? So this particular segment is really computing W given T equal to hot. And this part is computing probability W given T to be cold, right? And also we can specify a value for the condition variable and leave the other uninstantiated. And we can compute similarly as we did earlier the conditional probability like this. So we are specifying a value from this family, right? So these are the kind of different ways of looking at the joint distribution and deriving other probabilities, right? So let us take this example to illustrate the two algorithms that we have talked about, computation by enumeration or inference by enumeration and inference by variable ordering, right? So you have got rain, bad weather, and late for class. So if it is raining, so that means this is a bad weather. And if this is a bad weather, you might be late for class, right? And these are the kind of CPTs that are associated with these nodes. I don't think that I should explain this. This is very clear from the earlier discussions, right? So this is basically PR. This is P B given R, and this is P L given P, right? Now let us first try to illustrate the idea of inference by enumeration, right? So the first thing that we'll be doing will be looking at this particular structure, R given B and R relation, right? Now, if we multiply these two, what we'll be getting? We'll be getting probability P. So we'll be getting probability RB, right? So how do we do that? So take this row and multiply this row with this row. So if we do that, we get this R, B both to be positive and multiplication value is 0.008. Now, how do we compute this row? We take this row and multiply this. So it will be R negated B 0.002, right? So we are multiplying this value. Now let us take this row. And if we try to multiply with this particular row, we are having this joint distribution between not R, B. It will be having the value multiplication of this and this. And finally, for this, we'll be getting 0.81. And it's a joint distribution, right? So if you multiply these two, we get a joint distribution between R and B. And basically what we are doing here, we are performing a join operation over R. It is a kind of database join that I think if you have done database courses, so you have a common column on which we are doing this join operation, right? So as a result, we are collapsing these two to come up with a single node B and R, right? Now we have got RB and the dependent node is L, right? Now what we'll be doing, we'll be again performing a join over B, right? As we perform join over B, so again what we'll be doing, we'll be taking this row and multiplying this row with this row. And if we do that, we'll be getting the entry for R, B, L all to be positive. And only thing that we'll be doing, we'll be multiplying this probability to get 0.024. And we can do the same for the other row combinations. So we'll be doing this with the other values, this with the other values, so on and so forth. And as a result, what we are getting the joint distribution of R, B, and L. And of course, if we add them up, it will be giving you the value of 1, right? So now what we get the joint distribution over P, R, L, and B, right? The next task we'll be doing is the summing out operation or the marginalization operation, right? So this is an example of performing, say, sum out operation on R on this particular table. So I think we have derived this table earlier. So this table, probability, hello? Hello? So here we are performing marginalization over R, right? Now, if we do this marginalization over R, so how we'll be doing this? we are getting this value and this value. We are summing out on R. So that means we have to take all the possible values for R, right? And all the possible values for R is either positive or negative, right? And we take the corresponding values. And if we add them up, this will be giving us the probability that B is positive, right? And similarly, if we take this and take this and try to add these two values, so this will be giving us the value for probability minus B. And that is what we are doing, the operation summation or sum out of operation over R, which is also called marginalization on R, right? Now, if we perform marginalization over R on this joint distribution that we have already got, we'll be getting PBL. And then if we perform sum out operation on B, we'll be getting PL. Now, if we try to see what exactly we are kind of doing, first of all, we have computed the product of these three factors by performing two joins earlier. So first we did the join of these two, and as a result, we get a factor, and we find the product of that factor with this to get the joint distribution PRLB. Now we are performing sum out operation on R, and the sum out operation is represented by this summation R. And then finally, you are doing the sum out operation on B to compute probability of L, right? So this is what we do in inference by enumeration method, right? Now, in the contrary, in variable elimination, what we do, we perform a join and eliminate operation in an interleaved way, right? So we first join, then we eliminate, then we go for join, then we eliminate and keep on doing this. So let us take the same example and try to see what is the kind of computation that we will be doing if we perform this variable elimination to compute the same quantity, that is probability L, right? So the first thing that we'll be doing, we'll be taking this CPT and this CPT. And this CPT is PR, this CPT is PBR, right? So first we'll be performing a join operation. If we perform join operation on R, we'll be getting PRB. Then we'll be performing a sum out operation on R. If we perform sum out operation on R, we get PB, right? Now what we have again, we have got PLB, which is associated with this node, right? Now we perform a join operation over these two factors, and as a result, what we get PBL. And finally, what we'll be doing, we'll be performing a sum out operation on B to get PL, right? And what is the kind of expression that we are evaluating here? So first we compute the join of these two, right? Then we perform the sum out. So this sum out is related to this. Then as a result, we get this, right? Then we perform a join operation between this and this. So this operation is being represented by this. And finally, we perform a sum out operation on B. So you can see that the kind of computation that we are doing, the order of computation that are doing, that is having a one-to-one association with the kind of factorization that we have talked about, kind of variable ordering that we have talked about earlier. Great. Now let us try to compute a conditional probability from the given example. So here we are interested into compute probability L given R, right? So basically we are given with the positive value of R. So this is positive value of R. So this R is no longer a variable. We know that R is positive. So as we are setting R to be positive, we do not need to represent negated R. So this is stricken off, right? Now again, this probability B given R will also be stripped because these negated R rows, they will be gone, right? Now, if we perform the join operation here on R, what we will be getting? We'll be getting the joint distribution of probability positive R and B value, right? And this is the kind of matrix that we are getting here. Now we'll be performing a join operation on of this and probability LB. Now, if you do that, what we will be getting? We'll be getting this to be multiplied with this to be multiplied with this to be multiplied with this, and this to be multiplied with this. And finally, what we get? We get probability LRB, the joint probability LRB. Now, what we can do here, we can perform a sum out on B. Sum out on B. If we perform sum out on B, we get the joint distribution probability LR, right? Which is this. Now, from the joint distribution, I can easily compute the conditional just by normalizing. We can get the conditional distribution, right? So I think that we are kind of at the end of the very basics of probabilistic inference. So what we done here, we have tried to model uncertainty and belief with the notion of probability, and we have used the conditional independence assumption to factorize the joint probability in an efficient way, right? And that kind of structure gives rise to a kind of network of different variables, random variables, which we call as Bayesian network. And we can perform exact inference on the Bayesian network using variable elimination as well as inference by enumeration that we have talked about earlier. But you see, even though we perform these, in the worst case, we cannot avoid this 2 to the power n kind of complexity, right? So for that, there are different algorithms that have been devised, and those are approximate inference algorithms, right? So they may not compute the probabilities exactly. What they can do, they can sample some of the observation and come up with an inference. And the category of algorithm, in this category, the algorithms we can talk about is Monte Carlo simulation or Gibbs sampling. Those are the kind of advanced techniques. And those are kind of approximate techniques. And this Gibbs sampling is a very important technique that is being used in today's deep learning and machine learning algorithms very widely. And Monte Carlo technique is also used widely. One thing that we have not considered really is that random variables, we do not really consider notion of temporality between the random variables. If you talk about words in the sentence, if you talk about whether a particular word will be occurring or not, given we have seen, say, n number of words earlier. So there is a sense of temporality or sequentiality between these random variables. Now, whenever we will be trying to include time or sequentiality in our Bayesian network, we need to do a different kind of computation. And those kind of computations are done using models like hidden Markov model or dynamic Bayesian network, right? So with this, I like to end this module. I wanted to work on a couple of examples. Maybe what I can do that, create a video out on those examples and share the videos with you. I think from the next week onward, Professor Sudeshna Sarkar will be taking the lectures. I think she'll be starting with the planning algorithm. But I'll be working out a couple of examples on the computation of Bayesian network and share the videos with you. So I think I'm done for today. If you have any doubts or questions, I'll be happy to answer. But again, if you have any doubts in future, you can write me over email, or maybe you can ping me on the MS Teams. I'll be happy to respond. Thank you.
Sir, what will be the submission format for the interim progress report that we have to submit?
Okay, that we will tell you. So that will not be that involved. So it will be kind of it depends on there will be different format for project and assignment, the video topic presentation.
Sir,
So
Okay, sir. Fine.
We will be sharing you the format.
Okay. Thank you, sir.
Okay. So anything else?